This is the second part of our lecture on paired samples t-test. So this section is going to be focusing on the formula and the idea behind doing the paired samples t-test. So a few things to know, a few things to orient ourselves before we begin. So when we are doing a paired samples t-test, one thing that we want to be very careful of is to make sure that our data are paired. So when we are running a test in JASP or wherever, even if we're just doing it by math, we want to be very, very careful that the data are actually paired up with each other. So using our example of testing the amount of statistical knowledge maintained during class versus 1 year later, um, for subject 101, they scored a 100% on their stats class during the class, and then I follow up 1 year later and they dropped down to 88%. Subject 102 went from 90 to 74. Subject 103 went to 80, from 80 to 60. So I want to be very, very careful that if this is subject 101, that only their data are paired up with each other. This entire row is just subject 101's data. What I don't want to see is things getting unpaired, things getting disconnected, where, subject 101, they got 100% during class, but then for whatever reason, I kind of lost track of who was who. And so I just put, randomly, here's scores for a year later. So what's ending up happening is that subject 105 score, who got a 30, is now paired up with 101. So when I do my calculations, and when JAS would do the calculations, what it would look like is that this person is dropping by 70%. They forgot 70% of the material, when in reality, they only forgot 12% of the material. So very, very different conclusions based on that. So we want to be very, very careful to make sure that, each person who participates in their study, that this data is linked on the same row. I think that's just good general data cleaning and data science in general, but very, very important for how we are doing the paired samples t-test in particular. So for doing the paired samples t-test, the things that you will need to know. First, you need to know the null and the research hypothesis. This will kind of give us some orientation for what we're testing and what we're comparing. The second step is we will need to calculate the difference between scores for each of our participants in the sample. For number 3, we need to figure out on average how much did each person differ. And then finally, to give us context for what that average difference means, we have to understand a little bit about the variability in the sample through that estimated standard error of our different scores. Another thing to mention with this paired samples t-test, I know sometimes in the stats class and intro stats, I'm going to be throwing a lot of different tests at you. It's going to be a lot of different things throughout and through the end of the semester. And sometimes students get kind of confused because, we learned independent samples t-test, single sample t-test, paired samples t-test. And sometimes people treat it as like 3 completely independent, different tests. I would note here that they're basically all building off the same formula. Each one is just going to be a little bit different. So what we're testing when we're doing a t-test is the difference between means divided by that measure of error or variability. So it's literally the same concept. The only thing different here for the paired samples t-test is that mean difference that we're looking at is a within subjects mean difference, comparing you to you and seeing, how you differ across conditions. So our terminology here that we'll use in our little symbols, the M sub D is the mean difference, the mean of the different scores. And then this SMD is the symbol for the estimated standard error of the different scores. So want to note, I think some people also mess this up on the test. Sometimes people are tempted to plug the mean into these things and the different scores into these things. This is just a symbol. All this means is the estimated standard error of the different scores. So just keep that in mind. This is also something, as we talked about with the independent samples t-test, we're switching over to mostly using JAST for doing these. So the important thing is not necessarily to memorize these formulas, more to just understand the concept behind it and then understand how JAST was using these numbers to get the t value and the p value. All right, so let's get into it. Let's have an example of what a researcher might do with this paired samples t-test. So say we have this setup, we have this researcher, they're interested in emotion and cognition. So they want to know whether people have a better memory for positive versus neutral words. So the researcher gives participants one list of positive words. You can see here the positive list is all these nice warm fuzzy words like caring and friend and reward and comfort and things like that. And then they also get a neutral list, and these are kind of just like whatever words: carpet, ladder, pillow, napkin, whatever. And the researcher is trying to see whether people have a better memory for the positive list versus the neutral list. And so the participants are given a couple minutes to memorize these lists. Then they go and do some filler tasks and things that might take up your memory so that it makes it a little bit harder. And then 15 minutes later, the participants are asked to recall as many words as possible from these lists. And what the researcher is going to do is the researcher is going to compare the average number that you remember from the positive list to the average number that you remember from the neutral list. So our first step is to simply state the null and the research hypothesis. So for this, the null hypothesis, similar to all the other ones we've done, the null hypothesis is that there's nothing here. There's no difference between the positive and the neutral. And so what we would expect to see in this case is that you're going to be exactly the same. It doesn't matter how many words you remember in this case, because remember that this paired samples design kind of controls for that in a way. So if you're you have really poor memory and you only remember one word from the positive list, well, that your memory still applies to the neutral list, and so we would expect 1-to-1, and same for somebody who remembers all 15. But the main thing here is that there's no difference between the conditions. You will remember the same amount from list 1 to list 2. And if we look across the entire sample, we should see that same pattern apply. There's literally no difference between the conditions. The average difference between the positive list and the neutral list is going to just straight be 0. Now, the research hypothesis, on the other hand, is that there is a difference between the two conditions. And here we have a non-directional hypothesis. I guess this researcher doesn't really have an idea about whether the positive versus the neutral words would be remembered differently, or one being higher or lower than the other. So this is our research hypothesis. Just, there is an effect of the emotion on memory. So there's going to be some sort of difference. Either people are going to have worse memory for the positive words, or they're going to have better memory for the positive words compared to the neutral ones. So we start off, we set this up, we have this in order so that we can move forward and actually test out, when we look at our data, which one does the data support? Does it support the null hypothesis that there's no difference, or does it provide more evidence for the research hypothesis that there is a difference between conditions? All right, so now what we have to do is we move on to the second step, which is just to calculate the difference scores for each participant in the sample. So say I do my study, I collect my data, and this is what I get. So I have 5 participants in my study. I test them on their memory for neutral words or memory for positive words, and I get the following data. So participant number 1 remembered 9 words from the list, 10 words, 8 words, 9 words, 7 words. And then I look at the memory for the positive words, and I see participant 1 remembered 12 words, then 2 remembered 2 words, 9 words, 10 words, 11 words, and 11 words. So what I'm going to do now is I'm going to first start off with subject 1. And I'm going to see what was the difference for subject 1 for their memory for neutral versus positive words. And what I see here is I just calculate a little different score. Here I did positive minus neutral. and I get a value of 3. So basically, they're remembering 3 more words in the positive condition versus the neutral condition. Same thing for number 2. They remember 1 word less in the positive word versus neutral. This person remembers 2 more words. This person also remembers 2 more words. This person remembers 4 more words from the positive versus the neutral condition. So one thing I will note here is that the order that you subtract is fairly arbitrary. Remember that these are a nominal variable. So nominal just means name. There's literally no rhyme or reason for which one was number 1, which one was number 2, why I subtracted this from this. The only thing is that you just have to be consistent. Once you decide that you're subtracting this from this, just do that for everything. If I had done it the other way, I would have gotten the same numbers, but the signs would have been reversed. So this is another thing with that. Same with our independent samples t-test. The sign doesn't necessarily matter. It's more the magnitude that we care about. But anyway, what we do is we have all these different scores. We add them all up and we get a sum of 10. And then to figure out on average how many words did the sample remember from the positive versus neutral condition, we just take the average, take that sum of our different scores divided by the number of scores that we have. So in this case, it's 10 divided by 5, and our average is 2. So what this is telling us is that on average, people in this sample remembered 2 more words in the positive list versus the neutral list. All right, so we have that established, but now what we have to do is think about what does that average of 2 actually mean? This again is one of those things that sometimes people who are just starting off with statistics get tempted to look at the difference and say, oh, 2 seems like a lot, so it's significant. But we always have to remember that we don't have enough context to vibe out what is a significant mean difference based on the mean alone. We also have to incorporate the idea of variability and that idea of standard error. All right, so our last step is to figure out that idea of variability. So we have to estimate the standard error of the different scores from the different scores themselves. So this is a good example. This is from the textbook. So we're kind of deviating from our positive and negative word list example. They used something about self-efficacy, but this is a good kind of imagine that this is about the word memory. But basically what we see here is when we look at the different scores, we get a distribution. Some people are going to vary quite a bit. Some people are going up +5, some of them are going down 4, and then some people are not going to differ at all. So we're going to see a distribution here. And this is what we can do to estimate the standard error. So we can estimate this, take this difference and get a measure of like standard deviation and use that to estimate in the population what would this actually look like. So how do we do this? So basically we can figure out the estimated standard error by finding the standard deviation of the different scores and then using that good old standard error formula that we learned in previous classes. So here are our little formulas. So our sum of squares, going to be pretty much the same thing as what we learned when we were calculating standard deviation. However, in this case, we're using the different scores rather than the raw scores. So you'll see a D here instead of an X like you might be used to. But it's the same principle. We're taking a person's different score minus the average different score, square it to get rid of those negatives, and then add it all up. Then to find the variance, we take the sum of squares divided by n, but n minus 1 in this case because we're working with a sample and we want to have that little bias correction because we're usually leaving out people from the population. And then finally, we do the standard error of that mean difference. We can either just plug in this the value that we get for our variance, or we can take the square root first and then do it later. But basically, it's the standard deviation divided by that square root of n. All right, so let's just have a little walkthrough. So we have our different scores. What we have to do is we have to look at what we found for the average difference score, which if you remember, it was 2. And then we see how much did this person's difference score deviate from the average. So this person, they scored 3 more words from the neutral versus positive. The average difference was 2, so this person was 1 higher than the average. This person was -1, so they are 3 points below the average, and that should have a negative there. Oops. Then we have these two people that are like right smack on the average, and then this person who is 2 up. If I remember to put the average, the negative sign here, you would note that if you added all those up, it would equal 0. So, we talked about that, and hopefully you remember that from our standard deviation. Every time we do these different scores, it always adds up to 0, and that's not useful to us. So we square it, get rid of the negatives, and if we were to do that, we would get a sum of squares of 14. So then we can plug it into our formulas. Our variance would end up being the 3.5. So our sum of the standard error of the mean difference would end up equaling 0.84. Again, the formulas aren't necessary to memorize here. They are building off what you already know, but again, JAS will be doing this for us. The main concept is just understanding that we're looking at this variability in the different score and kind of quantifying how much variability there is in the sample. Our final step is going to be to put it all together so we know that our mean difference, our average difference between our conditions was 2 words. We also know that our estimated standard error of this difference, so the amount of variability in our sample is 0.84. So if I plug it into my equation, my numerator is going to be those 2 words. Denominator is going to be that estimated standard error of 0.84. And if we do this, we should get a t statistic of 2.38. Cool. So what does that mean? Well, we can use that t statistic that we just got to determine the p-value or the probability that we would have observed this particular pattern of results if our null hypothesis was true and there was actually no difference. So I found this p-value by just using JASP. That's the easiest way to do it for a t-statistic. If you remember when we talked about t-statistics, the value, the critical value is going to differ depending on the sample size. So it's easier to just either use an online calculator or to just use JASP to figure out the exact p-value. But if we did want to go old school and figure out the exact critical value, we could potentially use a t-table to figure that out. I realize I did not actually show you that when I mentioned that when we talked about the independent samples t-test. So I'll show you now. Basically, we have this is what the t-table looks like. So how you would use this, I'll see if I can use my little highlighter here. Do a highlighter. You would go and look on this up here and find where the value is 0.05. So here we had a two-tailed test, a non-directional hypothesis, where we didn't necessarily know which way our effect was going. So what we want to use is this column right here. The other ones are if you had other criteria for your p-value, you wanted to get, more confident that you're not making a type 1 error, or less confident. But this is going to be the main column that we're going to be using. I guess if we had a one-tailed test, we'd use this one. The other ones are kind of useless. So then we go find our degrees of freedom. Here we would see 4, and we would just do a little crosstab thing. One thing to point out here is, with this table, you can see how the numbers are changing from the sample size. If we only had 2 people, we would have to get a t-value of 12.7 to be statistically significant, which is kind of crazy. With 4 people, we need to hit a t-value of plus or minus 2.776 to reach statistical significance. And what we can see here is that with our value of the 2.38, we're kind of close to it. We can see the p-value is 0.75, but ultimately that's greater than 0.05, our cutoff. So you would say it's not statistically significant. Also with the t-value, it's falling into this little category here. So again, that's evidence that this is not statistically significant. Yes, there is a difference, but it's basically not enough for us to be confident enough to reject the null hypothesis. So we're going to retain our null hypothesis and say that there is no difference. Part of that might be because we only had 4 people. If we had more people and this pattern continued, we'd probably creep down lower. But in this case, we would retain our null hypothesis. So basically, our critical value is higher than our obtained value, or I guess I should say in this case, the critical value is more extreme than our obtained value. We would retain the null hypothesis. So a bit of a conceptual summary. What we'll see is that if we want to reach statistical significance, we'll want to have a higher t-value. And I'm using this t obtained as a symbol that that's the t-statistic that we get in our output. So what we will see is that this t-value, it will be larger if we have 1 larger mean differences. So that means our numerator will be larger. So just as an example, this was the thing that we started off with. We might see if we do a study, we might actually see that people really don't change. In this case, a lot of people are basically the same or like 1 word more from the different list. And so when you sum it all up, the difference score is 3. And so the average increase, the average change between the neutral and the positive word list, we would divide that by 5. So it would be 0.6. So our t-value is going to be way smaller than it was previously. So larger mean differences, higher numerator, more likely that we can reject the null hypothesis. Another interesting thing that we see, and this is true for a lot of different tests, but especially important for the this kind of paired samples design. Sometimes when we run our data, we can sometimes see this case is kind of weird where it works for some people increase, some people decrease. So this is an example. Say we have this person, they remembered 9 neutral words, but 6 positive words. Their difference score is -3. This person remembered 10 neutral words, 9 positive words. They're -1. But these 2 people, this person gained 2, this person gained 4. And so if you add all these up, it ends up summing to 0. So basically our denominator is 0 and there's just basically no difference. So one very important thing to keep in mind is that not only are we looking for differences, but we're also looking for consistent mean differences. Now, I will also note we will learn a little bit later a test that might actually reveal what's going on here. There might be something a little bit more complicated, but in terms of a paired samples t-test, if the scores cancel each other out, we're going to have to retain the null hypothesis because there's no mean differences. I mean, you can imagine if you were, reading a research paper and just trying to figure out whether positive or neutral words are easier to remember. And you read the study and they're like, well, some people remember positive words better and some people remember neutral words better. No clue why. You're like, thanks, that's not helpful, right? So we want to see large mean differences, but we also want to see consistent mean differences where everything's kind of going in the same direction. There's this clear pattern that, for instance, positive words are being remembered better than the neutral words. So these consistent mean differences, not only if they're in the right direction, they're going to increase that average difference score, but it's also going to decrease the denominator. If we mathed this out, we would see that the denominator would be a lot bigger because we have way more variability. We're going down from -3 to +4, whereas with here, we were only going -1 to +4, and basically everybody was kind of clustered around that 2 versus, here. And then the final thing, as always, we tend to see that the larger sample sizes will lead to a larger t-value because it's going to decrease that denominator. There's always or almost always less error when you have a larger sample size because it's more representative of that actual population. All right, last thing I want to mention is that the p-value will tell us whether something is statistically significant or not. We do also want to think about the effect size, which will tell us a little bit about the magnitude of the difference. Is it small, medium, or large? The same guidelines apply as we discussed with both our z-test and our independent samples t-test with the Cohen's d. So what we're doing here is we are kind of the same procedure. The mean difference here, again, is that difference for within each participant, the average of it. So the estimated Cohen's d, it would be, I guess that's supposed to be a 2, um, divided by the square root of our standard deviation. So we would have like a 1.5, which would be a very large effect size. That's something interesting. Sometimes we see with very small sample sizes, we can have something that doesn't reach statistical significance but still be very large. That's a good note that these are two different concepts, related and helpful pairing together. But sometimes you have very large effect sizes that don't reach statistical significance when you only have 4 people in the sample. All right, so that is what we are going to be talking about today. That's it. So feel free to let me know if you have any questions. There's another quick little learning check after this, so please take a look at that quiz and fill that out. Next class period, we do not have class all of next week. We are on spring break, so have a happy and safe spring break. I hope you have the chance to relax and potentially do something fun. When we come back, we will get to walk through paired samples, t-test, and JASP. We'll get to learn about all the different things that we can do with it and how we can interpret the data and how what we learned in class is associated with the formulations that JASP was going to do behind the scenes. All right, as always, let me know if you have any questions, and I hope you have a lovely spring break.